First of all, let me all thank you for coming here today. Around 32% of the failures of satellites are due to thermal failures. And why does this happen? This happens due to ineffective thermal control mechanism. Our research paper aims to reduce this, and here I am today to talk about how orbital parameters can affect the heat loads of a satellite. Before starting, I'd like to give an overview of the presentation. The presentation is structured according to the golden circle model proposed by Simon Sinek. It talks about why, how, and what of the presentation of the research. Introduction. I'm Sujan Bhargava and I'm a sophomore at IAC College of Engineering, Bangalore, India, studying aerospace engineering. I work as a subsystem engineer for a student space technology team called as Team Antariksh. Our major focus or emphasis while writing this paper was on Cubesats. And why do we need a thermal control system for a Cubesat? The Cubesat will be subjected to a variety of heat loads in orbit, and we need this to ensure the components of the spacecraft remain within an acceptable temperature range. Problem statement. We can break this area into the four fields. That's the problem, solution, the solution which we proposed, the purpose, and the procedure. A large proportion of small satellites are destroyed in orbit due to poor thermal control designs. Proper understanding of variation of heat loads with the variation of orbital parameters is very important for a thermal engineer to design a thermal control mechanism for a satellite. Orbital parameters such as the angle, altitude, and a few surface properties of satellite mainly determines the temperature of the satellite at a given instant of time. Now, through this research, we aim to understand how some orbital parameters such as beta angle, altitude, and surface properties affect the surface temperature of each of the 6 sides of the 2U Cubesats with our internal components, which is a hollow model. The results obtained from the simulation and the answers can be used to design a better thermal control mechanism. So the first few slides are the very basic ones, just to brush up the basics. Since we all know there are two major thermal control mechanisms and two approaches for thermal control mechanism, that's active and passive. And these are the 6 orbital parameters which determine the orbit. The semi-major axis defines the size of the orbit, eccentricity decides the shape, inclination signifies the orientation, tan signifies the trajectory of the orbit, the trajectory of the body, and the two anomalies signifies the angular position. And the orbit which we have considered is LEO orbit. So the major heat loads which act when the satellite is in LEO orbit are solar flux, albedo, and planetary IR. Beta angle. Beta angle is like the minimum angle between the orbit plane and the solar vector, and it can vary from -90 degree to plus 90 degree. And it influences the percentage of time that a satellite spends in LEO orbit in direct solar rays, and in the shadow region. Now coming to the methodology. The two main softwares which we used to get the modeling and the simulation done are ANSYS and Thermal Desktop. The model which we chose was a 2U Cubesat, a hollow one with dimensions of 10 into 10 into 22.7 centimeter, which is the standard dimension of a 2U Cubesat. The material which we chose was aluminium because it's lightweight and a strong material. And the spacecraft was used to create and mesh the 3D Cubesat CAD model. Thermal analysis of the Cubesat was done using thermal software. The surface properties and other orbital parameters and orientation has to be set in the thermal desktop to perform the analysis. When it comes to analysis, there are certain parameters which we consider to be constant and certain parameters to be varying. Solar flux was fixed as the 1370 watt, which is like the average value of the solar constant, and the albedo was considered to be 0.3 and the earth temperature was 288 Kelvin, and all of these data were taken from the NASA Earth Observatory website considering LEO orbit. And the parameter which we varied was the altitude which we have taken is 1100, 1200 and 1300 kilometers, as most of the Cubesats and small sats are launched in this particular range. And the data were also collected based on these 3 altitudes chosen. The beta angle we have varied it from 0 degree to 90 degree, and the inclination which we went was 0, 23, 45, 60 and 75 and 90 degree beta angle. The negative beta angles were discarded as a sign of the beta angle only signifies the direction of rotation revolution of satellite around the Earth and does not affect the results. Also with that, like, we consider two surface properties, namely the black polyurethane paint and the meta-OSR, the optical solar reflectors. Black paint was chosen because it has an emissivity of 0.81 and absorptivity of 0.94, and it can withstand aggressions of space environment and guarantee its functioning over a long service. And meta-OSR, the optical solar reflectors, has an emissivity of 0.79 and has an absorptivity of 0.16. It's very low, and this was chosen because it has high reflectivity, of course, and has low absorptance compared to other passive systems. And recently, like, those are used as quad tiles, but the tests are now being conducted with metal oxides such as zinc oxides. We had a video here of it, like, it's not playing, unfortunately. The orbit which we chosen was a fairly simple circular orbit with altitude defined accordingly. The constant solar flux albedo on the planetary IR was also specified in this. In our case, we have chosen like 1100 kilometers as an altitude. Individual simulations were done for each of the beta angles separately, and the temperature profiles for each phase of the satellite was plotted as well, which comes in upcoming slides. This animation depicts the temperature distribution of the satellite surface over one revolution, that is one complete orbital period, for every 100 seconds, and this helps to understand and visualize how temperature distribution varies throughout its evolution. These are the results which we obtained from simulations. First, I would like you all to think about the significance of these graphs over here. These graphs are for black polyurethane paints, the first surface coating which we used. Each line here depicts one altitude, that is, like, there are 3 lines over here, and each line depicts one altitude. The x-axis is the beta line, and the y-axis is average temperature. Average temperature here means that the average temperature of the middle node of each phase, which we had selected for the complete orbital period, and the average temperature for a node for 6,000 seconds, that is like 100 minutes. There are 6 graphs for 6 phases of the satellite. 1000, as we can see, 1100 kilometer has the highest average temperature, and the temperature decreases when with the altitude, but does not vary significantly, as the difference is just 100 kilometers, which we have seen. But the IR and albedo has very less and in fact negligible variation. The heat loads are like maximum in a range of 50 to 70 degree beta angle, and it's the same for all 6 phases, and the reason for that will be discussed in the conclusion part. The maximum average temperature occurs as 60 degree, and the minimum average temperatures are lowest at the 90 degree. We can also observe that this effect of altitude becomes negligible at beta angle 45 degree, because all the lines seems to meet at a point over there, and the same pattern is followed by all the 6 phases, and it's like zenith has the highest maximum average, that is like 283 Kelvin, and has the highest minimum average temperature too, which is very like 260 Kelvin. And the natal phase has the lowest maximum average and the lowest minimum average temperatures too. The similar trends have been like observed in meta OSRs as well, like it shows maximum average temperature at 60 and minimum at 90 as well. But we can observe that the temperature of all the phases are slightly lower than the black polyurethane paints. Even though the difference in absorptivity of both black paint and the metal OSRs are significantly high, the variation in temperature profiles in each phases isn't that significant, because the metal OSRs which are being used as quad tiles. This shows the temperature versus time for one orbital period, and the plots are for black polyurethane paint at 110 kilometers, 100 kilometers, sorry. The thick blue lines here are the combination of several lines, each of which indicate an element of the mesh. The variation is similar in every case of the altitude and the surface property, and the only maximum, minimum, and average values are varying over here. At lower beta angles, if you can observe, the difference between the maximum and the minimum temperature is comparatively large and decreases as the beta angle increases. The beta angle determines the percentage of time the satellite spends in direct sunlight and the shadow region as well. So in the conclusion part, as we saw from the results, the temperature doesn't vary much with the altitude is what we observed, and the beta angle has a significant effect on the temperature of each phase of the satellite. The maximum temperature, maximum external heat loss was observed between the range of 50 degree to 70 degree range, and as we observed, like zenith has the highest faces the highest load, and the nether faces the lowest load. And also the beta angle, as the beta angle increases, the satellite tends to remain more time in the sun illuminated area in its orbital period. And based on these results obtained, this can be used for designing better thermal control design mechanism for a CubeSat. It also gives any CubeSat developers a source to understand changes in space environment with a variation of orbital parameters. Also, based on these results, orbital parameters can be chosen accordingly while launching the CubeSat. The other thing, and for the future scope, we intend to the orbit which we considered here was a fairly simple orbit where we could have just changed two parameters, that's the beta angle and the altitude. And for the future scope, we intend to continue this research by taking a Keplerian orbit where we can vary other parameters, other orbital parameters like a RAM, orbital temperature, true anomaly, and checking the variation of temperature in each phase of the satellite.